Okay, so welcome to exam revision. This is our first official lesson. So this booklet is what we'll work through, at least for the next 3 lessons. Hopefully you've already had a dip into the PMI questions there. So in my absence Tuesday, I sent an email with this booklet attached to it, and I've got there basically one of every kind of PMI question that they can ask. So we've got divisibility, series, products, matrices, trig identities. And then the new technique that we didn't cover at the start of the year because we hadn't done much calculus yet was nth derivatives. So I've made a video about that skill in particular, and there's a number of questions there for you to have a crack at PMI with the nth derivative there. So that's a recap of PMI, and so then today that puts us at Thursday of week 9 if we're following our schedule on the front. So I might just, before we move on, I'll address this schedule and I'll talk about resources and the exam in general and so forth. So today my plan is to go through polynomials, functions and complex numbers. So that's what we did in most of term 1. All right, so we had a little bit of term 1 dedicated to PMI, but most of it was dedicated to polynomials, functions and complex numbers. Next Tuesday, I anticipate going through vectors, and that leaves the following Thursday to go through integration. We'll have a tutorial in the holidays where we'll go through an exam together. And then when we come back for term 4, we have lessons for the week 1, trial exam week 2, and then I'll have optional lessons in week 3 and 4. I'm going to recommend coming along. And the exam is Wednesday the 13th of November in the morning. So the methods exam is in week 4 on Monday, the spec exam's in week 5 on the Wednesday, so 9 days separation between them. Now I've got written down here, so I'm not in Mondays now, my timetable's changed, but if you want me to come in Monday to catch up with you, I'm very happy to. So I can shift things around, and basically I'll be attendant to you, so tutorials available at request. So you let me know if you want me to come in, if you've got some questions, otherwise just pop in during lesson time. Because we've got a small class, we should have plenty of time to address any questions that pop up. But I'm going to encourage you to keep coming in week 3 and 4 to the lessons. I'll be here. It'll be good to catch up, make sure you're doing a bit of work in those periods. Okay, so we'll just have a look at the revision resources. So here's a pretty comprehensive list of all of the exam revision resources. And most of these are accessible on the OneDrive. So we've all got the OneDrive link where we access the work solutions and practice tests and so forth. So I'll just take you through that. The first one I've mentioned there is the revision guide. So just like the methods course, the spec course has a revision guide. They don't publish a hard copy of it anymore. I have this one for you guys to have a look at today and pass around, and I can bring it to each lesson, and maybe you can negotiate with each other if someone wants to borrow it for a little bit, that's fine. So we'll have a look at that today, but you're invited to purchase an electronic copy of it. It's a pretty good resources. It's got a plethora of copious quantities of questions. There's so much in there to recap. So the revision guide, that's a good resource. Then basically everything else is on the OneDrive. So we've got all of our SATs, okay, 2017 through to 2023. We've got previous exams, all right, so the SACE exams. Again, just like methods, the spec course began in 2017, the updated version of it, the version we currently use. And so we have exams from 2017 all the way through to 2023. And it was the year 2020 when they changed it from a 3-hour exam to a 2-hour exam. Okay, so from 2020 onwards, we have 2-hour exams. Prior to that, we have 3-hour exams. Same content, they're just longer. So just keep that in mind when you're revising them. We've got the MASA exams, which are Maths Association of South Australia, so they're made by teachers like me. They're all to suit the course and so forth, so they're fine. QATS exams, we bought those for a couple of years, but we weren't very impressed with them. Like there's some sample exams from when they've first set up the course. There's the sample exam question sets, so sets 1, 2 and 3. Chief Assessor's reports, what that is basically after the exam's complete and the markers have all done their analysis, the Chief Assessor, that's the person who writes the exam, they have a look at the results and they talk about what students did well and what students did badly. And that can be quite useful in picking up handy tips for yourself, so you can make sure you're not making mistakes that students will commonly make. So we'll sort of draw those out in coming tutorials. Okay, then over the course of the year, I've given you a number of booklets on exam questions which are directly related to each SAT that we've done. So you've got a booklet already on PMI exam questions. And so those are all questions that I've plucked from old exams and formulated into a booklet. The same goes for polynomials and functions, complex numbers, vectors, integration, and differential equations. So you should have 6 booklets there, hard copies on exam questions, and their solutions on the OneDrive. We also have the old Spec Maths exams, although some of the questions there aren't relevant. Basically, there's lots of stuff here to work through. That would be your last port of call if you made your way to it. And the revision guide includes a lot of those questions that are relevant anyway. Okay, for the exam, it's the same as methods. You get 2 double-sided A4 handwritten sheets of cardboard. We'll provide you with cardboard, or maybe I'll go get it today because I've got it printed there to give to you. You also get the formula sheet. That's going to be provided to you, so you're not required to bring your own. That will be provided for you. It's 2 hours and 10 minutes. You can bring a graphics calculator and a scientific calculator if you wish. If you want the unit circle, you'll have to draw that on yourself. That's not provided for you. And we just want to make sure you're practicing the exam situation. So we've got under 2 months till the exam. So it's 19th of September now, 13th of November is the exam. So just under 2 months to the exam. Plenty of time to study, but we're going to treat it like a marathon. We've got lots of practice exams. So we should be trying to hit, sort of a SACE exam once a week between now and then, sort of 8 weeks to go. All right, so any questions about our general summary there of exam revision? All right, so marathon, not a sprint. We're just going to keep hacking away at it in preparation for the exam. Yeah, so just in weeks to come, we'll be, well, this week and next week, we're week 10 next week, we'll be recapping the unit. So if we flick then to SAT 2, so we flick the page, we've covered PMI, we're at polynomials and functions. Now what I would suggest next week, if you haven't done so this week already, is maybe you can bring your notes book that we did for chapter 2, chapter 3 and chapter 4, bring those along. And basically I'd just like some feedback from you guys now, is how instructive do you want this to be? Like, we did polynomials a long time ago, so maybe a useful thing to do would be to go through these questions together. Okay, let's do that. So it's going to be a bit of a stretch for me as well. Let's get straight into it. So if we're talking about SAT 2, that was where we did polynomials. So that was in our textbook, chapter 2, and functions. And so we start with operations with polynomials. So that's basically multiplying polynomials together. We talked about zeros, roots, and factors of polynomials. That's exercise 2b. We know that if we have a function p of x, if a is a 0, then p of a will equal 0. So let's get into an example here. And with this example, this is quite a long-winded example, but maybe we'll just set up and show you how we can solve this pretty easily. We have this cubic polynomial, 2x to the 3 plus 15x squared plus 24x plus k. It has 3 linear factors. 2 are identical. That means one of them is a squared factor. So we have this cubic polynomial, and it's equal to some linear factor. We've got 3 linear factors. Like, we could write it like this. X take a times x take b times x take c. But 2 of the linear factors are identical. So that means like one of them is going to be squared. All right, because it's a double root. And the other thing we should anticipate is we have this 2 out the front, which means we need to have a 2 out the front here somewhere. But maybe we'll just put it there, 2x take a. We could have it out the front here, but maybe we'll just chuck it in that one. That would be nice and easy to solve. All we would need to do is expand everything on the right-hand side and equate the coefficients of each term. All right. Do we want me to go through further than that, or that sort of makes a bit of sense on how we would go about that? So maybe it's probably good I've set up how to do it, and I'll leave that for you guys to have a crack at, expanding this and equating a bit later. So there's a bit of space there for you to work through. Question 1, that's polynomial form. Okay, let's get on to division then. So in exercise 2D, we looked at 3 different processes for division of polynomials. 2 different processes. We looked at the division algorithm and synthetic division. So let's go through both of these then. So if we've got our first one set up, it's 4x to the power of 3, take 6x squared plus 7, all on top of x plus 3. Now the division algorithm is the one that we set up like this. We put x plus 3 here, and then we list the terms present in the polynomial here. Take 6x squared. Now we have 0 lots of x, so we need to include that, right? We're going x3, x squared, x1, and then we have the constant term. So that's how we set it up for the division algorithm. All right, and then we ask ourselves, what do we multiply by x to get 4x to the power of 3? And the answer is 4x squared. Okay, 4x squared, I'm going to write that above the x squared term. 4x squared times x gives me 4x to the power of 3. 4x squared times 3 gives me positive 12x squared. And then we subtract it away. All right, so 4x3 cancels. Minus 6 take 12, we have minus 18x squared. And then we repeat, what do I multiply x by? Okay, x is our leading division term. What do I multiply x by to get minus 18x squared? It's going to be minus 18x. So minus 18x times x. Minus 18x times 3 will be minus 54. Subtract it away. Okay, then what do I multiply x by to get 54x? Positive 54. 54 times 3, what's that? 162. Okay, so when we perform a division, right, we have the polynomial, we have the divisor, we have what we're dividing it by, d of x, so we have the polynomial, d of x, we have the divisor, and that's going to leave us with the quotient and then plus the remainder.
It's the remainder over d of x.
Yeah. So this is what's left over. So let's identify what are the components we have here. This is the polynomial that we started with. Okay, that's p of x. This is our divisor. This is d of x. This is our quotient. That's what we get when we divide it. And then whatever's left over down here is our remainder. So they're all of the parts that make up the polynomial division. So that's A. I'll leave B for you guys to have a go at if you want to. B's are a little bit more complex. We just have a few more terms here, right? So we're doing quadratic division there. So that's the division algorithm. Let's refresh synthetic division. Are there any questions about the division algorithm? Or remembering that? Good. It's a useful tool. Okay, so we have 2x to the 4 take 5x squared plus 4x plus 2 divided by x plus 3. So the way we set up the division algorithm, the synthetic division algorithm, is we've got divided by x plus 3. So we're going to put minus 3 here because that's the root of x plus 3. And then we're just going to list the coefficients of the polynomial. So if we have 2x to the 4 take 5x squared plus 4x, so the leading coefficient is 2. Then we have 0 lots of x to the 3, and then we have minus 5 lots of x squared, positive 4 lots of x, and then the constant term is 2. We draw that square bracket off there, don't we? We always put a 0 here. We start with a 0 here, and we go 2 plus 0 is 2. And then we multiply this number by this one. 2 times minus 3, minus 6. 0 plus minus 6, minus 6. Minus 6 times minus 3, positive 18. Positive 18 and minus 5 will be positive 13. 13 times minus 3, minus 39. Okay, so that's much faster when we're dividing by a linear term. That only works when we're dividing by a linear term. But what we have, here's the coefficients of our polynomial. Here's our divisor. This here is our quotient. All right, so we have 2x to the 3, 6x squared, 13x, our constant, and then we have our remainder of 107. Okay. All right, so that's 2D, that's polynomial division. All right, let's flip the page over. We'll recap the remainder theorem and the factor theorem. We've got examples here. Okay, for the remainder theorem, we have when a polynomial is divided by x take k, has a remainder r, then p of k equals r. Find a, given that when p of x, so we have x squared plus ax, x squared plus ax take 5, is divided by x take 1, the remainder is 4. Okay, what this means from the remainder theorem, p of 1 equals 4. So we're going to put the number 1 into the equation here. So we'll have 1 squared plus a take 5 equals 4, and we're solving through for a. So what's that? 1 take 5, that's minus 4. That's on both sides, 8. Okay, just to restate that, if this is the polynomial, x divided by x take 1, the remainder is 4. Therefore, p of 1 equals 4. So we can put the number 1 in and solve for a. The factor theorem is very similar. For any polynomial p of x, if k is a 0, then x take k is a factor, which means p of k equals 0. Find a given x take 1 is a factor of this cubic polynomial. So we have x to the 3 take 7x squared plus ax take 9. And we have x take 1 is a factor. Now what it means is p of 1 equals 0. It's a factor, which means it's a root. So 1 take 7 plus a take 9 equals 0. And we can solve through for a. So we got there minus 16, minus 15, minus 15. All right, then we have, we've got p of x is a real cubic polynomial. Now we have one factor is 2 take I. All right, one factor is 2 take I. Find a real quadratic factor of p of x. So if 2 take I is one of the roots, then the other root is 2 plus I. One of the other roots is going to be 2 plus I. And so the sum of these roots, when we add these roots together, 2 take I plus 2 plus I, we'll get 4. And the product of these roots, if we multiply them together, we'll have 2 take I times 2 plus I. Difference of 2 squares. 2 squared take I squared. I is the square root of minus 1. So I'll do this in a sort of drawn out method. So we have 4 take away the square root of minus 1 squared. Square root and squared will cancel, so we have 4 take minus 1, 5. Basically, whenever you have take I squared, you just got plus 1. Alright, so we have 2 take I and 2 plus I. These roots have a sum of 4 and a product of 5. So that means the quadratic factor that is composed of these two roots is x squared. Take the sum plus the product. Alright, so we have a quadratic factor, x squared, take the sum plus the product. Alright, then in 2i and 2j, we're really looking at using our calculators to graph polynomial functions. A lot of it's sort of year 11 content, stuff where we've got like, we're crossing the x-axis here. They're going to be the roots, if that's a, b, c. And we have x take a, x take b, x take c. If it's if it touches, it's a squared factor. All those kind of things. All right, so let's have a look at question 7 then, because then we moved on from chapter 2 to chapter 3, where we started talking about functions. So it says, consider the function the square root of x, and g of x is 5 take 2x. Find g of f of x, so find the composite function.
F of g.
F of g of x, sorry. So that's going to be the square root of 5 take 2x. Alright. And state its domain and range. Okay, so firstly for domain, this function is going to exist provided this part is greater than or equal to 0, right? We can't have the square root of a negative number. So the domain is 5 take 2x has to be greater than or equal to 0. And we're going to solve this inequality through for x. Now inequality is almost the same as equals. So the first thing we're going to do is subtract 5 from both sides. And then we're going to divide both sides by -2. Now whenever you multiply or divide by a negative number, the inequality reverses direction. Alright, now this is something you could observe from the graph as well. If you graph this function, you'll see it only exists for values of x that are less than 5 or 2, less than 2.5. Okay, so that's its domain, and then its range. Alright, again, if we graph a root function, we're not going to have the root of a number will never equal a negative number, so it's always going to be positive. But we have y is greater than or equal to 0. It's either 0 or positive. Good. Alright, so that's 7. Alright, the inverse functions. This was an important one. So we have y equals 3x plus 2. And I'll just talk quickly, what's an inverse function? So remember the line y equals x. An inverse function is just a mirror image about the line y equals x. So the classic example is e to the x and ln of x. They are inverse functions. They're the mirror image of one another. Now, we have the function y equals 3x plus 2. So if we're going to sketch that function, that would look something like this, I suppose. 2's here, I'm just going to sketch 3x plus 2. And so the inverse function is going to have the opposite properties, and it's going to look like that, I suppose. Now, if we have y equals 3x plus 2, that's the equation of the function, and we want to find the inverse. The easiest way to do that is via variable interchange, which is where we swap x and y. And we solve through now for y. Alright, so I'm going to subtract 2 from both sides, and then divide both sides by 3. Now, the properties of inverse functions, right? So the y-intercept becomes the x-intercept, the x-intercept becomes the y-intercept. Yeah, so each coordinate swaps, doesn't it? All right, so sketch the function, sketch its inverse, part A, part B. So part A, part B, part C. Just find the function. Good. Okay, then in 3C we did reciprocal functions, we did reciprocals of other functions. So we have the quadratic function f of x equals x take 1 times x plus 2. And the first one says, find the reciprocal function and state its domain and range. So the reciprocal function is 1 on f of x. That's 1 on top of x take 1 times x plus 2. Now, in our notes book, when we talked about the different types of functions, reciprocal functions and absolute value functions, we have a list of dot points that talks about the properties of what happens to these. So it's things like, if you think, as we're approaching a root, roots become asymptotes, don't they? Because a root is when the function equals 0. If we have 1 divided by 0, that's approaching a math error, that's where we have an asymptote. So we have a list of all of those properties, and of course we can just graph the function to observe those as well. So find the reciprocal function and state its domain and range. Well, for its domain, we know that it's not going to exist at positive 1 and minus 2. That's where the asymptotes are occurring. Now the graph of the function will look something. So we have asymptotes at positive 1 and minus 2. Alright, and we have local, this originally, it's a quadratic that's originally opening upwards. Okay, so originally it's a quadratic that was opening upwards, it has a local minimum. And so we have local minimum is going to become a local maximum here somewhere. And so it's got these kind of features. That we go as we go x approaching positive infinity and negative infinity, we can see that's going to get closer and closer to 0. So we expect a horizontal asymptote there. I'm not sure about this maximum point. Let's find that, because with this quadratic, let's find it algebraically. Okay, so this is going to be x squared plus 2x take x take 2. So what's that? X squared plus 2x take x. So plus x take 2. That's what it expands to, right? Now remember, the turning point of a quadratic occurs at minus b on 2a. So this is the x value. So what are we going to have? Minus 1 on top of 2, minus half. All right, so that's the x coordinate of the turning point. Now if we want the y value, we can sub into one of these, I suppose. So let's do that. Y equals minus half take 1 and minus half plus 2. So this is going to be minus 3 on 2 multiplied by positive 3 on 2. We have negative 9 on 2. Alright, that's the y value on the original function. However, the reciprocal function is 1 divided by negative 9 on 2. Okay, it's 1 divided by the y value. So that gives us negative 2 on top of 9. Okay, so now we can answer the range question. Alright, so I've found this local maximum value here. And I also know that it's asymptotic to the x-axis, because as x approaches infinity, all right, this number gets really large. We have 1 divided by a really large number. We're approaching 0. So here's our domain, here's our range. Y is less than minus 2 on 9 and greater than 0. Okay.
Would y not be negative 9 on 4?
Like this, not square something.
Negative 3 on 2 times 3 on 2, is that not negative 9 on 4?
Oh yeah, good. Good pick up, yep. So negative 499, good. And so yeah, when we're talking, so that's the y value of the original function. When we're talking about that maximum point, it's the reciprocal of it, isn't it? We have 1 divided by. All right, all of that we can get from our graph anyway, but it's useful to draw these things out algebraically. All right, flip the page, then we have absolute value. Okay, so this is going to be a good recap for us for absolute value functions. So we have define the following algebraically and graph. So we have y equals the absolute value of x plus 2. So this is how we define it. We say it's going to be positive x plus 2 if x plus 2 is positive. And it's going to be negative x plus 2 if x plus 2 is less than 0. Alright, so that's the definition that we have for absolute value. Alright, positive, whatever the absolute sign is around, if our value is positive, and negative x plus 2. And so we can simplify all of that a little bit, so let's simplify it. So we have x plus 2 if x is greater than minus 2, and we're going to have minus x take 2 if x is less than minus 2. I'm going to sketch both of these so we can draw out how we've got that function. And again, you can use your calculator, but it's useful to recap the skills involved in doing it manually. So x equals minus 2, that's going to occur here somewhere. So I'll go x is 1, x is 2. Now for x is larger than minus 2, we have the function y equals x plus 2. So that's the equation of a line that has a slope of 1 and a y-intercept of 2. It's going to look like this. Okay? It doesn't exist down here because we have absolute value, which means it's always positive. And then we have the function minus x take away 2 if x is less than minus 2. So for values of x less than minus 2, it's got negative slope and a y-intercept of minus 2. So its y-intercept would be here. So it's this line, right? But exists to this side of it. Okay, so we can draw that to help us consider what it looks like, but that's what the absolute value function looks like for y equals x plus 2. And we can get that again straight from the calculator.
How would you label that on the graph?
This function here, y equals modulus x plus 2.
Yep.
Yep. All right. Okay. Question 11. Given f of x is x squared plus 5x, graph f of x, modulus f of x, and f of modulus of x. So I'll just do that quickly. If we have x squared plus 5x, right? Think about like, again, think about how we do these things without our calculator. X times x plus 5, so its roots are 0 and minus 5. So what that means, here's 0, here's minus 5 somewhere. It's a quadratic, it's opening upwards. That's what the function looks like. All right, it's got some minimum. Now, if we're going to do the modulus of f of x, this one's very easy to do. All we're doing is making every negative y value positive. All right, so what that means, it's going to look like this. All right, so you just make that component positive. And then f of modulus of x, we discard everything. I just need to check which side we discard. Discard everything either to the right or the left. Can't remember. Anyone remember? C must be f2. F of modulus of x. Discard the graph for x is less than 0. Okay, so for f of modulus of x, all right, we're going to discard the graph for x is less than 0, and we just mirror that. So f of modulus of x looks like this. Excellent. All right, and then we have solve a absolute value equation. Okay, so if we have 2x take 5 equals 10, modulus of 2x take 5 equals 10, well, that means it could be positive 10 or negative 10. So we go 2x take 5 is plus or minus 10, and then we solve by find the solution. So over here we get now what that means as well, like I'll just sketch a graphical solution for you. If we graph 2x take 5, it's going to be x is greater than 5 or 2 here. So if we sketch the line y equals 2x take 5, and we've found when does it equal 10, all right, when does it intersect with the line 10, you can see with negative 2.5 and the positive 7.5 there, minus 2.5, positive 7.5. So we can find those graphically as well. All right, pointing out a connection there. All right, so that's chapter 2 and 3. Do we want to take a little break before we go through complex numbers, or should we keep powering ahead? Power ahead, let's get it done. Okay. So, complex numbers. All right, I'll just do one of these. We have a complex plane. We have 3 plus 2i. So it says find z plus w. So z is 3 plus 2i, and w, like George W. Bush, is 1 take 4i. And so we have z plus w. All we're doing is adding the real parts together and the imaginary parts together. So just like, you know, you're doing your horizontal and vertical vector components, we're doing our real and imaginary components. So we'll have 4 and minus 2i. And it says sketch it on the card on the argand plane. This is a special name for argand or complex plane. We're going across 4 down to I. So 4 down 2. This is the real axis. This is the imaginary axis. And so, so here's the complex number. That's what it looks like. It has direction. Okay, so you can do B and C yourself. Or maybe just quickly, conjugate. So you're asked to find Z, W conjugate. W conjugate, that just means change that symbol, doesn't it? So where 1 take 4i, it means it becomes 1 plus 4i. So you're just flipping the sign on the imaginary component. Okay, let's go. Question 2, find the modulus and argument of minus 1 take 2i. Okay, so modulus, that's just the square root, and it's the real component squared plus the imaginary component squared. So we have a modulus of root 5. And the argument is just tan theta of the imaginary on the real. What's that, 53 degrees or something? And shift tan 2, tan 2, 1.10 radians. All right, so that's question 2. Question 3, on the argand plane, sketch these regions. So we have the modulus of z being less than 2. Now what would that look like on an eigenplane? If this is our real axis and this is our imaginary axis, and we have a complex number such that the modulus is less than 2. It's not equal to 2, it's less than 2, so it has to exist somewhere in this region. So we're colouring in, that's loci in the complex plane. That's part A. And then if we have, and the real part of z is greater than 3. Alright, so what that would look like is our plane, here's the modulus of 3, and the real part has to be larger than 3. Sorry, I'm mixing up modulus and the real component. It's going to look like this. This is the real axis. Here's the number 3. And the real part has to be larger than 3. That's better, isn't it? It has to be anywhere such that the real component is larger than 3. Because we're just focusing on the real rather than it being about the modulus. All right, so that's basically an intro to the Cartesian plane. Let's move on to polar form then. We have the complex number root 2 cis pi on 3. Z equals root 2 cis of pi on 3. Now we'll recap exactly what this means and so forth in a moment as we draw it out. It says state the modulus and argument. So the modulus is always the number out front. So the modulus of z is root 2. The argument of this complex number z is pi on 3. Sketch it on the Argand plane. So here's an Argand plane. It has a modulus of root 2, so that's its length, and an angle of pi on 3. So that's what it will look like. My pi on 3 is not in a good position, sorry, I should adjust that a little bit. Pi on 3 is more up here. Pi on 3 and root 2. And then lastly, find in Cartesian form without technology. So remember, there is a button on your calculator that lets you just alternate between the two forms, polar form and Cartesian form. But the way we're going to convert it is cis of pi on 3 means cos of pi on 3 plus I sine of pi on 3. Now on the unit circle, cos of pi on 3 is positive half, and sine of pi on 3 is root 3 on 2, and we'll just distribute the root 2. Alright, and so there I've just multiplied the root 2 into the root 3. Now let's apply some skills with polar form, because it's particularly useful for multiplying and dividing complex numbers. Okay, so when we have cis A times cis B, they're going to multiply together. It becomes cis pi on 6 plus pi on 2. And so what's that? We change that to be 3 pi on 6. So we'll get 4 pi on 6, which is 2 pi on 3. Okay, use De Moivre's theorem to find the exact value of 1 plus I root 3 to the power of 7. So what we're going to do here is we're going to convert this from Cartesian form to polar form first, 1 plus I root 3. So we want to know the modulus and argument. Now the best way to do this is in your calculator. You can type that in and just press the buttons to convert it to polar form. So let's see if I can remember how to do that. We go 1 plus I root 3 and option, complex, cross arrow. Yeah, so what you do, option, complex, press the cross arrow, and then there's this one, which corresponds with F3, which is that R and B. And so that tells you the modulus and the argument of any complex number in Cartesian form. So convert it, and I've got 2 angle a third pi. So what that means is 2 cis of pi on 3. Okay, so that's the complex number in polar form, and we're asked to convert 2 cis pi on 3 to the power of 7. We're asked to find its exact value. All right, so that's going to be 2 to the 7 cis of 7 pi on 3. So that's de Moivre's theorem, which we then use. We've got 2 to go. Well done, we've steamrolled it. Which we then use to find the nth roots on the eigenplane, finding the nth roots and plotting them. So we have z to the power of 3 equals -1. Now, if I want to express the number -1 as a complex number, so -1 is here, so the real part is here, which means my a is positive pi. So this is cis of pi, isn't it? So we have z to the 3 is equal to cis of pi. Okay. Then what we'll do is we raise both sides to the power of the third. So we'll have z equals cis of pi to the power of the third. And so this is where we have z equals, cis of pi. I should put my plus k2 pi here. The k is 0, 1, 2. Pi on 3 plus k2 pi. K is 0, 1, 2. And then we'll solve through. So we get z equals cis of pi on 3. And k is 0. And then we'll have pi. And k is 1. And then 5 pi on 3. Which we need to convert to minus pi on 3. Because technically, the argument of z lies between minus pi and positive pi. Alright, so that's outside the domain of in the positive direction, so we need to consider it in the negative direction. So they're the 3 roots of unity of -1. So if we sketch them on the Cartesian plane, on the eigenplane, I'm going to draw it as a circle. We have minus pi on 3, positive pi on 3, and minus 1. They're the 3 roots of the complex number -1. Do you remember finding those kind of things? Yeah. Then we have loci in the complex plane, and this one I might just set up for you guys to solve. Because again, this is a fairly sort of long-winded one once we get the algebra sorted. So we have sketched the locus such that the modulus of z plus 3 is equal to 2 times the modulus of z take I. Now z is some complex number such that x plus iy is equal to z. So that's what I'm going to do first. Okay, and then what we're going to do is, well, modulus means the square root of the real component squared plus the imaginary component squared. So we can write that out as the square root of the real component squared. This is the real component. This is the imaginary component. And then same over here. The real component plus the imaginary component. And then all it's a matter of doing is squaring both sides and solving through for, it's going to be the equation of a circle. May involve needing to complete both squares. Do you want me to keep going or? Yeah, alright. So what we'll do, we'll square both sides. That's going to be 4. So we're going to just need to completely expand everything so we can collect all the terms together. So we have x squared plus 6x plus 9 plus y squared, 4x squared plus, and that's 4y squared plus 4. Alright, collect all the x's and y's on that side, that's our positive side. So then we have 3x squared, take 6x, and we'll have plus 3y squared, and 8y, and then we have 4 and minus 9. 4 minus 9 minus 5. Alright, then we're going to complete each square. Now, how do you complete the square when it's got a coefficient? I remember how to do it with this mnemonic. Alright, let's try. So we've got 3 times, this is going to be x squared, take 2x. Now the way you would complete this square is you'd add half of b squared. Alright, but then because you've added it, you need to subtract it. So let's just keep it in brackets and do it like that. It's going to make it nice and easy. So add half of b squared, and then we have to subtract it. Because we've added it, let's find that it's in brackets. This part is going to complete. So that would be 3 times x take 1 squared, and then we have take away this 3 here. Yep. And what are we going to do over here? We have 3y squared take 8y. Well, we can still pull 3 out the front and y squared. Take 8 on 3y, and we add half of b squared. So that's going to be nasty. This is where it's going to get a little bit nasty. Plus 8 on 6 squared, and then take 8 on 6 squared. And close the bracket, and then there's that take 5. That's still there. Alright, and so then that's going to complete to y take 8 on 6 squared, and then take away 3 lots, 8 on 6 squared, and then take 5. Alright, so almost done. We have this 0 over here because we moved everything over. Alright, and so what we'll do, let's shove all of the numbers over to the left-hand side and then divide it by 3, and we've got the equation of 2 circles. So plus 3, plus 5, and then plus 3 lots of that. So we've got 8 plus 3 lots of 8 on 6 over here. And on this side, this is a nasty one. And then when we divide both sides by 3, we have 8 on 3 plus x take 1 squared, 8 on 6 squared. Okay, we'll evaluate that. what's that going to be?
16 on 9.
16 on 9? 16 on 9? Awesome.
Well, it would be, what, 64 and 36?
Plus,
Oh, no, I just did the square thing.
oh, that one? Yeah. Plus 8 on 3. Yeah. Anyway, what we have here is the, excellent, 88 on 27. 88 on 27. What we have here is the equation of a circle. Okay, so I'll just recap to you. Equation of a circle, x take a squared plus y take b squared equals r squared. So the centre of this circle is 1 and 8 on 6. We can simplify that. And the radius is the square root of 88 on 27. So that was a pretty nasty one. I think I just made up the numbers, which is why sometimes they work out like that. But the process remains the same, okay? For that kind of question, you're finding the equation of a loci in the complex plane that satisfies this. So if you sketch that circle, that makes it such that the complex number z plus 3 is equal to 2 times the modulus of the complex number z take I. So what did we do? We subbed in x plus iy for z. We collected the real parts and the imaginary parts. We performed the modulus of both sides. We fully expanded, moved everything over to the right, and then what I've done down here is I've collected the x parts and I've started completing the square. Now, how do you complete the square? So if we focus on this 3x squared takes 6x, I want to complete the square. What I'm doing is pulling that 3 out the front, and I'm looking at this, and we always add half of b squared. So b is minus 2, so we add half of it, and then square it. And because we've added it, we need to subtract it. Okay, so we're maintaining equality. We're not changing the value of this quadratic. We've added it, so therefore we need to subtract it. That part is a perfect square. X squared take x to x plus 1, equal x to x take 1 squared. Then distributed the 3, so it distributes to the squared part, and that minus 1 out there. Did the same over here, although it was a little bit more complex. Shove the numbers over, divided by the 3, equation of a circle. Pretty nasty one, but we got there. All right, so how are we feeling about that sort of recap of